Hey math stars, do this bell ringer, pause the video, and start playing after you finished it. All right, so as you know, the general term in a Taylor polynomial or a Taylor series is the nth derivative of f at c x minus c to the n over n factorial. This is on the AP test. You need to know it. So the third degree Taylor polynomial centered at x equals -2 is 2 plus 3x plus 2 to the first power over 1 factorial. The next derivative is 0, so we can skip that one. Plus 5x plus 2, now this is the n equals 3 term, x plus 2 cubed over 3 factorial, or you could put a 6 there. Okay, second bell ringer question. Given the fourth degree Maclaurin polynomial for g of x, which is p of x equals 2 minus 4x plus 7x squared minus 4x to the 4th minus 5x to the 4th, find g double prime of 0 and the fourth derivative of g at 4. So we're using this expression I wrote up here for the general term in a Taylor series, except let's call it g this time. So if I want the n equals 2 term, it's going to be g2 of 0, x minus 0 to the 2 over 2 factorial. Basically, since it's Maclaurin, I knew that it was centered at 0. And since I see the double prime here on the left-hand side, I see the double prime, that tells me for that term, n is going to equal 2. So I'm going to set that equal to the 7x squared. Now let's just do some canceling. So let's cancel out the 7x squared, or cancel out the x squared. Then let's multiply the 2 factorial to the other side. So g2 of 0, which is the same as g double prime of 0, is equal to 7 times 2 factorial. So g prime prime of 0 equals 14. Okay, next, g to the fourth, or the fourth derivative of g evaluated at 0. So again, I'm going to do the fourth derivative of g evaluated at 0, x to the 4th over 4 factorial. So that's the n equals 4 term. I'm going to set that equal to the negative 5x to the 4th. Cancel out the x to the 4th to both sides, and let's multiply that 4 factorial over to the right. So the fourth derivative of g at 0, multiplying that 4 factorial over, we get negative 5 times 4 factorial. Don't need to simplify numeric expressions. If you did, this 4 factorial would be 24, but you're welcome to leave it as negative 5 times 4 factorial. Okay, so real quick, I just want to talk to you about what's on the AP test this year. So as you know, they've cut down the AP test quite a bit, and there's only 5 sections in the Unit 10 that you need to know. So the first one you need to know is 10-2, working with geometric series. Next, we need to know harmonic and p-series. Then also 10-7 and 10-8, and we'll learn those next week. And then out of all of these remaining topics, the only one that you need to know is finding Taylor polynomial approximations of functions. I plan to teach all of these topics so you have a complete knowledge of series, but the ones with the check marks are the only ones you need to know how to do on the AP test. So 10-2 we covered on Wednesday. 10.11, we've covered that in the last few weeks. So that's similar to that first question on the bell ringer that we did today. Basically anything where you're using this to formulate a oops, come on. It doesn't like that I'm touching the screen with my hand also. The nth derivative of f at c, x minus c to the n power over n factorial. You need to be real comfortable using that with that section 10-11. Okay, let's move on to today's lesson. So the integral test for series is not on the AP test, but you're going to hear about p-series and harmonic series today, and those are on this year's AP test. So for a function that is continuous, positive, and decreasing, and we have some function f of n, which is equal to the terms in the series a sub n, then either both the series and the integral, they either both converge or they both diverge. For example, if I had, say, this series n equals 1 to infinity of 1 over n squared. We'll look at that a little bit later in the notes. If I wanted to use the integral test with that one, I would find a very similar series that's continuous, positive, a very similar function of x that's both continuous, positive, and decreasing. So this function, 1 over x squared, if you think about what the graph looks like in the first quadrant, because we're only going from 1 to infinity, it looks very similar to the graph of 1 over x in the first quadrant. That past 1, that is a continuous function, it's positive and it's decreasing. So we could go ahead and try to evaluate that integral. And you probably remember from our study of improper integrals whether this guy converges or diverges. But if you don't, we'll revisit it in a little bit. But if this integral happens to converge, then so does the series. That's the basic concept of the integral test. Let's look at this first example. Who are we going to compare him to? What function are we going to compare him to? We're going to compare him to the function x over x squared plus 1. Let's kind of think about that function. So we're starting at n equals 1. So if I were to think about this function for x greater than or equal to 1, well, he's never undefined for anything greater than or equal to 1 because the denominator is always positive. So he's continuous. Also, this function is always positive, any x value I plug in greater than 1. And it's always going to be decreasing because the bigger x value I plug in, this denominator is going to increase more quickly than the numerator. And so this guy would approach a limit of 0. That would be a decreasing function every time I pick an x value greater than or equal to 1. So this function is continuous, positive, and decreasing for x greater than or equal to 1. Good. That has to be true in order to proceed. Now we're going to integrate that from 1 to infinity. The integral test is not on the AP test this year, but very likely you could see an improper integral. So let's go ahead and integrate. So we're going to, before we do our u substitution, let's rewrite this as the limit as b goes to infinity. Integral from 1 to b of x dx over x squared plus 1. Okay, now doing our u substitution, u is the denominator, so du is 2x dx. Okay, in order to proceed with our u substitution, let's multiply inside by a 2, in the front by a 1/2. Okay, substituting, we get 1/2 the limit as b goes to infinity Okay, let's go back and look in our integrand. Well, the 2x dx goes away and becomes du. In the denominator, we're going to have u. I left some room there because we're going to change our limits to be in terms of u also. So our new upper limit, remember we're plugging these limits into the expression for u. So plug this in here for x. So our new upper limit is b squared plus 1. Our new lower limit, plugging a 1 in there, we get 2. All right, let's integrate. So the 1/2 stays in front. Limit as b goes to infinity. Integrating, we get ln of the absolute value of u. Draw your vertical line, write your limits. So this becomes 1/2 the limit as b goes to infinity of ln of b squared plus 1. Don't need absolute value because that function is always positive. Absolute value would be fine, just unnecessary. Minus ln of 2. Okay, let's think about the function ln of x. Well, the function ln of x is an increasing function, always. So as we go to infinity, ln of x, as x goes to infinity, ln of x would also go to infinity. Let's go back here. B squared plus 1 is always increasing as b goes to infinity. And so we'd have an increasing function, and then we're taking ln of an increasing function. So the limit of this function would be infinity. So this guy equals infinity. Or in other words, he diverges. Does not have a finite value. So what does that tell us? So that tells us, therefore, this series, n equals 1 to infinity, of n over n squared plus 1, diverges by the integral test. Okay, let's move on and try another one. This is a difficult test just because improper integrals are difficult. Okay, next one. So this guy, let's relate him to the function 1 over x squared plus 1. This function is continuous when we're going from 1 to infinity. It doesn't have to have a 1 here at the bottom, but we usually start the integral test with, you could start with n equals 2, n equals 3, n equals 4, and that would just be the lower limit on your whatever integral you use. So that function is always continuous. It's always positive in the denominator. It is always positive, no matter what x value I plug in. And it's decreasing. As x gets bigger, the overall output would be smaller and smaller. All right, let's do the integral test. So let's go over here to the left. So we're going to be taking taking a look at this next series. There's a couple things we want to look at first before we decide which convergence test to use. So we want to first see if the nth term test applies. So if I were to find the limit as n approaches infinity of 1 over n squared plus 1, well, when n goes to infinity, the denominator is going to get really big, and so this guy's limit would approach 0. The nth term test does not apply. It only helps us when the limit is something other than 0. So we can't use the nth term test. If we think about the geometric series test, that only works if our series looks something like a times r to the n power. In this series, n is not n is not the exponent, so we can't use the geometric series test either. Then you want to consider, does this 1 over n squared plus 1, does that resemble a function that we could integrate? And this does look like an integral that we can evaluate. So let's go ahead and try the integral test. First thing we need to do is determine whether this function is continuous, positive, and decreasing when x is greater than or equal to 1. The reason I care about x greater than or equal to 1 because I'm starting with n equals 1. So this graph is never undefined. The denominator never equals 0, so he's going to be continuous. It's always positive. Any input for x, always positive since I'm squaring and adding 1. And it's always going to be decreasing. Every time I pick a bigger x value as I move along the positive integers or the positive real numbers, the function would be approaching 0. So it is always continuous, positive, and decreasing for x greater than or equal to 1. If that's the case, then I'm going to go up here and evaluate the improper integral from 1 to infinity of 1 over x squared plus 1. So that would equal the limit as b goes to infinity of 1 to b, 1 over x squared plus 1 dx. Okay, so integrating this, we get the limit as b goes to infinity. Arc tan x, and then we're going to input a b and a 1. So hopefully you recognize that this was the derivative of arctangent of x, so we can easily integrate that there. Okay, let's continue and plug in. So we have the limit as b goes to infinity, arctan b minus arctan of 1. So to evaluate those arctangent values, it's helpful to think about the graph of tangent x. So the graph of tangent x has vertical asymptotes at negative pi over 2 and pi over 2. The graph of tangent x can be drawn in like so. Okay, so when we evaluate arctangent, we're looking for the value of x at which tangent has an output approaching infinity. So when we evaluate the first part of this limit, we want to determine the value of x where tangent approaches an output of infinity. Well, that's going to happen on the graph here when it approaches that asymptote at pi over 2. So this is just going to turn into pi over 2 here. And then you know from the unit circle that at pi over 4 and 5 pi over 4, tangent is equal to 1. But when we evaluate arctan, we're only looking between negative pi over 2 and pi over 2. So subtracting this integral, this improper integral, is going to be equal to pi over 4. So if you recall what we learned when we studied improper integral a month or two ago, is this graph of 1 over x squared plus 1, if we were to determine the area to the right of x equals 1, beneath that graph, this area would equal pi over 4. So what does that tell us? Well, since our integral converges, therefore we can conclude that the series from n equals 1 to infinity of 1 over n squared plus 1 converges by the integral test. So this justification we did had a whole lot of evidence. We spent a long time working on all of this evidence, and then our claim and our reasoning were real quick at the end. Let's take a look at these 3 examples on the top of your screen. These are not series, but they're improper integrals. As you recall, when we have an improper integral, from 1 to infinity, 1 over x to the p power, it converges when p is greater than 1. So this first example, p is equal to 1. This one diverges. Integrals of the form 1 over x to the p diverge when p is less than or equal to 1. They only converge when p is greater than 1. The next one, well, cube root means 1/3 power. So p is equal to 1/3, so this guy diverges because, again, p is either less than or equal to 1. And the last one, p equals 5, so p is greater than 1, so this one converges. So this leads us to our fourth test for convergence for in infinite series. So we learned the nth term test, the geometric series test, the integral test, and the p series is very, very easy to look at and determine convergence. So normally the lower limit on our integral is 1, but this middle integral, I put a 2 here. Doesn't matter what the lower limit is as long as it's some positive integer. Same thing with an infinite series. It doesn't really matter what whole number we start with in our series. What determines convergence is what happens when we move out toward infinity. So it doesn't matter if we start with n equals 6, n equals 1, n equals 2. This thing is either going to converge or diverge based on the value of p. So this is what our series looks like for a p-series test. And again, it's going to converge when p is greater than 1. It's going to diverge when p is less than or equal to 1, similar to the improper integrals. One more quick little tidbit. The harmonic series is a special kind of p-series. It's the one where p is equal to 1. So n equals, doesn't matter where we're start counting, n equals 1, n equals 3, n equals 4. But the harmonic series is 1 over n. So inputting that 4, it's 1/4 plus 1/5 plus 1/6 plus 1/7. And so since this is the p series with p equal to 1, this guy diverges. So the harmonic series is just a special name given to this, and it's a series that you need to know diverges. Okay, so what was today's lesson about? Today's lesson was determining convergence using the integral test, by using p-series, and by using the harmonic series. And if you see a p-series question or a harmonic series question, really you don't need to show much work for your evidence. You just need to say what p is, and then either it converges because p is greater than 1 or diverges because p is less than or equal to 1.